Hello everyone, welcome to our new video. In this video we will continue with the Cramer's rule in solving a system of linear equations. In the previous videos we talked about the Gaussian elimination method. Now we continue from here. So we are given a system of linear equations represented here. We have the constant coefficients a11, a12, a1n, and notice that we have n number of unknown variables denoted by these x1 to xn, and we have n number of equations. So it's a complete system in the sense that the number of unknowns equals to the number of equations, and we write down the matrix of coefficients. So the matrix of coefficients is denoted by A, and the elements of this matrix are given by these A, I, J terms. And then the vector of unknowns is given by X, and the right-hand side values are given by these B values. So in compact form, we can represent this system as A times X equals to B. So in the Cramer's rule, actually the solution for xi is given by the determinant. So this is the determinant of the coefficient matrix, but the ith column is replaced by this vector b. So the ith column, you need to find the ith column in your coefficient matrix A, and then replace that ith column of A values with this b vector, and then divide this with the determinant of A. So this will give us a scalar, a number, that's the solution for xi. And if we repeat this for all the x values, then we find the solution of this system. So this is called as the Cramer's rule. And here's an example. So suppose we are given a 3 by 3 system, 3 unknowns x1, x2, x3, and 3 equations. So it's a 3 by 3 system. And first we can go ahead and calculate the determinant of the matrix of coefficients A. And remember how we write this matrix of coefficients. The coefficient in front of x1, that is 1 actually here. And then you have 4, 5, 4, 2, 5, you go to the second row, and then the third row minus 3, 3, and minus 1. So this is the coefficient matrix A, and you need to calculate the determinant of this A. We have already introduced how to calculate the determinant, so we don't need to repeat it here one more time. And this is, if you check this, this is equal to 29, which is not equal to 0. So we can go ahead and use the Cramer's rule, because if this is 0, then we cannot use this method. So the first unknown variable x1 is given by, as we said, you should use the coefficient matrix A, but for x1, the first column you should substitute with 2, 3, 1. So the first column of A here, this is the first column, this is replaced by the B vector, which is the right-hand side of these equations. And the remaining terms are the same. So this gives us the solution of x1. And similarly, this time to solve for x2 using the Cramer's method, we replace the second column with 2, 3, 1, and that's basically rewrite this coefficient matrix, take the determinant, and divide by the determinant of A. That gives us the solution for x2. And then similarly for x3, you repeat the same process and replace the third column with the right-hand side values, and then take the determinant, divide by the determinant of A. That gives us the solution for x3. So we can put all these together and write the solution of the unknown x. Okay, here is another example. Suppose this time we have a 2 by 2 system. X and Y are the unknowns, and use the Cramer's rule to solve this system. As usual, you will need to first write down the matrix A and calculate the determinant of A. 5, 6, 3, 4, these are the coefficients. The determinant equals to 2, which is not equal to 0, so we can go ahead and calculate X and Y. For X, you will need to substitute the first column by 12 and 6 here, and then take this ratio, we get 6. For the Y variable, now the second column should be replaced by 12 and 6, and then divide by the determinant of A, and this will give us -3. So this solves the system using the Cramer's rule. We have a few exercise problems, as you see here. I leave these as exercise for some practice by yourself, and we can move on to the next slide. Now we need to define the so-called adjoint matrix. Now we are coming towards the inverse of a matrix. We have seen the determinant calculation. The next thing we will talk about is the inverse of a matrix and how we can calculate the inverse. So in order to calculate the inverse, we first need to introduce the so-called adjoint matrix. And suppose we have the matrix A, which is m by n. And then the adjoint is defined in terms of these A, I, J values. And here you can notice that we have this m. So these m, these are actually the minors. These are the determinants of submatrices of the matrix of coefficients A. So we need to, each time, in order to calculate the adjoint matrix, for each entry, we need to calculate this determinant Mij and then multiply with this alternating plus or minus 1 values. And in order, we have a theorem here. This theorem simply actually says for an m by n matrix, the inverse of the matrix is given like this if the determinant of A is not equal to 0. Then we can actually calculate the inverse of a matrix. Here's one immediate example. Let's see how we can actually calculate the inverse of a matrix. So there are 3 steps in this question. The first one is just to calculate the determinant of A, which is, as we have already done before, we can use, for example, the first row. If we fix the first row, then I'm going to multiply 1 with the minor, the determinant of this submatrix, which is -2 minus 15 times 1. And then we will actually go to the second term and use this submatrix and calculate the minor. 4 minus 3, 5 minus 1. 4 times minus 1, minus 4 plus 15. That's the determinant. And we have minus 4. That's the coefficient. And then the third one, now you will need to look at to the, so let me use another color. Okay, so for this 5, now you need to take the submatrix here. Okay, you need to take this submatrix now, which is the determinant can be calculated as 4 times 3, 12 plus 6, that's 18 times 5. So altogether, the determinant of this matrix A equals to 29. So that completes the first step. And then the second step, this A, which is same as the adjoint. That means the adjoint matrix of A. This should be calculated. So these elements, A11, A12, A13, A21, A22, etc., you need to calculate these again from the matrix determinants. For example, for the first one, you are going to consider this determinant here, okay, which is minus 2, minus 15, which is minus 17 here. And then you will move on to A12. So A12, that actually comes to this point. So you need to use here these elements, take this submatrix, minus 4 plus minus 4 plus 15. Okay, so well, there's a small typo here. Yes, so this will be minus 11. The result is correct, but there's a small typo here. So this will give us minus 15, and don't forget that we have a minus 1 here. So it is minus 15 minus 4, that is minus 11 as a result. So we continue and then move on to, for example, A13. So for A13, you will be actually here, and the remaining, the minor is given. So that's 12 plus 6, that is 18, okay, here. So we calculate the adjoint matrix by calculating each of the entry, and then we are going to write them into our adjoint matrix. And in the last step, actually, for the inverse, as we know, we need to divide the elements of this adjoint A by the determinant of A. Determinant of A is already calculated, which is given as 29. So the last step here is simply, from the second step, we divide every element by 29, and we will get the inverse matrix. So as you see, once we complete this calculation of adjoint matrix A, in the last step, we just need to divide these elements by 29, basically. Here we have another example. We are given matrix A, and then for this matrix, we can calculate the determinant, minus 4, minus 6, that is minus 10. Because this is 2 by 2, it's relatively easy to calculate compared to the 3 by 3 case. And then how to get the adjoint matrix. Now, as we have done just before, for the adjoint matrix, we need to calculate the elements of these adjoint matrix one by one, and that is given for A11. A11 is this point, so basically that's the only remaining sub value here is minus 4. So we write determinant of minus 4 is minus 4. By the way, don't confuse this with an absolute value. This is the determinant sign, and the determinant of a constant, a scalar, is itself. So this gets out as minus 4. And here this is plus 1 because it is a square. What about A12? For A12 now you are going to use this value. The determinant of 3 is also 3, but this time this is cubic, so it will have a minus sign. A21, you calculate this again as minus 2. A22, you calculate this as equals to 1. So once you calculate these numbers, then the last thing we should do, now we write these values, minus 4, minus 3, minus 2, and 1. Okay? And then basically we divide by the determinant of A, which is minus 10. So you write minus 1 over 10 and minus 4, minus 2, minus 3, and 1. Okay. So you can simplify this a little bit more and obtain the inverse of the matrix A. We have again some practice questions for you. I have written this as homework, but This is you can consider this as an exercise and try to answer these questions, like calculate the determinant of this A, calculate the adjoint matrix A, find the inverse, and in the second question you should choose the right answer out of these choices. The third one again calculates similarly like the first one. Do these calculations one by one for the given matrix A. Here are a few more questions. Again, you can try to solve these by yourself. The fourth one is asking you to find the value of x and choose one of these multiple choices. Again, these are given choices for you. So these are multiple choice questions, and you need to do the calculation for the determinant in 5 and 6. Now we have a few more definitions to complete this part. So if we have n by n matrix A and A transpose equals to A inverse, then we call this matrix A as orthogonal matrix. Or we can write this as A transpose times A equals to A inverse times A. That should be equal to the identity matrix I. And if A transpose times A is giving us the identity matrix I, then we say A is orthogonal. And here is an example. We have matrix A. We calculate the A transpose. Basically, we can replace the rows with columns. This is 0, 1, 0, 1, 1, 0, 1, 0. And then we can multiply and we can check this condition. A transpose times A, we get the identity. So this A is orthogonal matrix. Let's consider another example. We are given the matrix A, and this is orthogonal because A transpose times A is also equal to the identity matrix. Now, if A is an orthogonal matrix, then the determinant of A must be either plus or minus 1. And notice that how can we verify this? Because we know that A transpose equals to A inverse. If A is orthogonal, we have this condition to be satisfied here. You can also just actually you can multiply both sides by A inverse. This is A. So you can also do this without changing anything in this equality. So we just rewrite it like this. And identity times A inverse, this is still, it gives us the same A inverse. So that means A transpose equals to A inverse for this orthogonality property. And if we take the determinant of both sides, remember, determinant of A transpose is same as determinant of A, and this is the 1 over determinant of A. So you can solve this and find that determinant of A will be either plus 1 or minus 1 as long as we have this orthogonal matrix. Here, if we are given another remark here, if A squared equals to A, then the determinant of A must be either 0 or 1. Again, you can simply check this by taking the determinant of both sides. This is the left side, right hand side. And we know that the determinant of A squared equals to determinant of A. Therefore, I mean, this is basically equal to this determinant of A squared, but we can factor out. We can factor out this guy, and this is determinant of A minus 1 equals to 0. So we have only two possibilities, either this 0 equals to 0 or 1. There's another special definition. This is van der Monde determinant. Basically, it is for these type of special form of matrix. The calculation of the determinant can be done by this product. So this is a general formula for an n by n matrix when we calculate the determinant. And here is a more specific example with a fourth order van der Monde matrix and determinant calculation. There is also some example for the third order. We can skip this one. And in the next example, we are given matrix A, B inverse, and C. And furthermore, we are given an identity that tells A inverse times X equals to B transpose times C. And given all this information, our goal is to calculate X. And notice, first of all, we can actually separate X first from this identity that is given. So if we multiply both sides by A, that will actually give us identity as the coefficient I times X, but I times X equals to just X. So we obtain A times B transpose C as our X value. And from here, we can notice that we are given B inverse here. And if we invert this B inverse, the inverse of inverse gives us the matrix B. So by simply inverting this 2 by 2 matrix, and notice that for the 2 by 2 matrices, the inversion is actually much simple. We swap these two terms. So we have 3, 2, and then we put a minus sign in front of the cross diagonal terms here. We put minus 4 and minus 1, and then divide by the determinant of this B. So we find matrix B by doing this calculation. And once we know what is B, and we are given A is okay, we found B transpose can also be calculated easily, and C is also given. So by just plugging in all these values here, we can solve X. So you need to do this matrix multiplication. You can multiply these two matrices first, and then you can multiply with this 2 by 1 vector. What is a symmetric matrix? The definition for a symmetric matrix tells us for a n by n matrix, if A transpose equals to A, then we call this matrix A a symmetric matrix. And you can immediately check with this example. 2, 3 minus 5, that's also same as the column. 3, 7, 6, 3, 7, 6, the same. And we have minus 5, 6, 1, minus 5, 6, 1. So A transpose equals to A. Another example, suppose we are given this A, and we are also given that this is a symmetric matrix, then we can easily calculate these missing values A, B, and C. Okay. For example, this value must be equal to the corresponding symmetric value. B should be equal to 0. A should be equal to this value 2. So actually you can see. And this C should be equal to minus 1. Because when we swap the rows with columns, if we interchange them, then this must be satisfied. One more definition here, which is to define antisymmetric matrix. An antisymmetric matrix property is actually given by this identity. A transpose should be equal to minus A. If this is satisfied, then we have an antisymmetric matrix. And as you see in this example, suppose you are given matrix A and matrix B, and you want to answer which one is antisymmetric matrix. And you can just directly check the definition. For example, take the transpose. The transpose is basically this 0, 9, 5, 0. This is transpose. And this is not equal to minus A. So this one is not antisymmetric. What about the second matrix B? Again, take the transpose. The transpose is given 0, 3, minus 3, and 0. But this is equal to minus times this B. Therefore, B is antisymmetric matrix. Another example to calculate the determinant of a matrix. And notice that all the rows are identical to each other. And for this type of determinant, we can directly say this is equal to 0. Because remember, we are allowed to do row operations. So for example, I can multiply the first row by minus 1 and then add to the second row. I will get 0, 0, 0. But if we have all zeros in one column or a row, the determinant is also equal to 0. Another example. Here, we are given a 3 by 3 matrix A. And if the determinant of A equals to 5, then what is the determinant of 2 times A? Now, remember, if we have a scalar multiplication within the determinant, then each row or each column is multiplied by the scalar 2. Therefore, we can factor out the 2 values 3 times, because for each row we can factor out the value here, which is 2 in this case, and this will give us 2 to the power 3 times the determinant of A. And since the determinant of A is already given as 5, this is going to be 2 to the power 3, which is 8, times 5 equals to 40. Now, another example. Suppose you have the augmented matrix given with this 3 by 3 coefficient matrix A. So the question is, what should be the value for the unknown B for a consistent matrix? And in order to find out this B, basically with augmented matrices, we usually do the row operations in order to get zeros in the below the diagonals. For below the diagonals, which is here, this is the diagonal. So for these 3 values, we want to get 0 by doing some row operations. And that's possible, of course, if we multiply the first row by minus 3 and then add to the second one. This will become 0. This will become here minus 6, minus 7, and minus 14. Similarly, you can multiply the first row by minus 4 and then add to the last one. And you can see this is what we get. For the actually this third column, you can notice that we can also write this as minus 6, minus 7, and divide this by 2. So we can actually we can simplify this expression. If we divide everything here by minus 6, so we divide this by minus 6, and then this is divided by also minus 6, which gives us, of course, 7 over 6. So that is given in the second column. And this is what we can get after we do this simplification, that is dividing everything by minus 6 here. And then for the other term here, once we get this 1, we can multiply the second row with minus 12 and then add to the third one. So if we do that here, after we multiply the second row by 12 and then add to the last row, this will cancel out to 0, and then this will also cancel out to 0. And here basically you will have 12 times 14 over 6, that is 28. So basically b minus 20 plus 28, that will give us the b plus 8 here. So in order this system to be a consistent system, basically the left side is 0. We also want this term to be 0. And that implies b equals to minus 8 for a consistent system. Another example, suppose we are this time given a 4 by 4 system, 4 unknowns and 4 equations, and how do we solve this system? Basically, you will, as usual, write down the, you need to write down the coefficient matrix A, and then this is the augmented matrix, A and B, when we write them together. This is the so-called augmented matrix. And from here, you will do your row operations in order to make sure below the diagonals, because we want these below the diagonal coefficients, we should get them equal to 0. And we can only achieve that by doing these row operations. For example, the first row we can multiply by minus 2 and then add to the second one. So this will be 0. Okay, this will be minus 2. This will be minus 3, minus 1, and minus 2. So that is written here after you do this row operation. Similarly, you can add the first row multiply by minus 1 and then add the second one, third one, sorry. So this becomes 0, 1, minus 1, 1, and 0. So we obtain this correctly. And finally, for the last one, we can multiply the first row with minus 1 and then add to the last row again, similarly. So these are 0, 0, minus 2, minus 1, and minus 2 in the last row. Now from here, we have a few more steps left because we also want to have ones in these diagonals. That will simplify our life. So we can actually swap the second and third rows with each other. So the third row goes to the second row goes to the third row, and we get this one and this one here. Now by doing this, we can multiply the second row by 2. If we multiply this by 2, we can easily add to the third row. So that will cancel this guy and make it equal to 0. And then this is minus 3 minus 2, that's minus 5, 1, and minus 1. And finally, for the last one, if we actually divide this by minus 2, this becomes 1, 1 over 2, and 1. Okay, now we are almost there. I mean, we are almost completing now. Now the thing we need is also we need to get this guy equal to 0 more easily. So we can swap again one more time the rows. This row goes to the below, and this one goes to the fourth. The third row becomes the fourth row, and vice versa. And that gives you the last row becomes minus 5. So we multiply the fourth row with 5 here, then add to the last one. This will become 0, okay, and then this will become basically 5 over 2 plus 1, that is 7 over 2 equals to 3. And here, this means 7 over 2 times our x4 equals to 3. Okay, so this implies 7 over 2 x4 equals to 3. So that means the x4 equals to 6 over 7. Okay. So we can then go ahead to the previous step and solve for x3, and then continue to the second row, solve for x2, x3, x4, and then finally in the first, using the first equation here, we can also solve for x1. So it's recursively we go, backward and calculate the previous x values. And as you see, we obtain a solution of these x values here. Another example, we are given the matrix A and B and C, and the thing we need to calculate is this expression, but it's a straightforward linear algebra question. You need to take the transpose of this C and then subtract matrix A given. So take the difference is given by this matrix, and then you need to calculate the inverse of B and multiply with this. So the inverse of B for a 2 by 2 case, it's not too bad. This is the determinant, and here you replace these two terms and put minus sign here. As you see, this is you replace this 4 and 0 and then put a minus sign, so this becomes 2 and minus 1. So this is minus 1 and 2. So basically that's the inverse, and finally you can calculate your x, which requires this guy times the inverse of B. The inverse of B is here, and this gives us the matrix that is given. Finally, let's see a few more properties of the determinant, and then we will finish the video. So in this example, you are given a matrix n by n, and if the determinant B equals to B, small b, then calculate these quantities in terms of the determinant of B. So determinant of B inverse, this is 1 over determinant of B, which is given by 1 over B. The transpose doesn't change anything for the determinant, that's still the same. Determinant of a cubic or fourth order, etc., then you can take the power of the result, then that's going to be b to the cube, b to the third power. If we have a scalar multiplication of the matrix B, then we can take out of the determinant by taking the nth order, nth power, sorry. And this is 2 to the power n times B as a result. And finally, determinant of B transpose times B, that is going to be, again, possible to separate them. This is B transpose B, but this is also the same. These two things are just identical. So this is also B, this is also B, so we get the result will be B squared. So we have done already quite many types of examples related to the determinant, and also matrix inversion is covered. Thank you for watching, and we will continue in our next video.